Hello, everybody, and what is up? It is your physics teacher here, Mr. Fabianski. I wanted to bring you guys a little help video, a little tutorial on how to fill in this sheet that I've given you called the graphs of motions compared. Okay, you'll find it in your class notebook. It looks a little something like this. It's got some text boxes on it. You guys will be able to type in displacement versus time graph, a velocity versus time graph, and an acceleration versus time graph. Anywhere the graph, or excuse me, anywhere the table has a nothing written in it, okay, you will not have to fill in anything into those areas. But anywhere there's a capital or a lowercase a, you will have to fill in stuff there. So let's quickly get all these things away. And then we can jump right into this. I won't take up any more of your valuable time because I know how much you guys are looking forward to figuring out physics. I have the board over here. I have the slope over here. And we're just going to move. I don't know what happened with my camera, but we're going to actually minimize this. And I'm going to go over to the board right here. And hopefully you guys will see me in just a second. So welcome, everybody. We're going to get some graphs up here. That way we can kind of see exactly what these graphs look like and how to pull the information for the sheets right over there for the y-intercept, the slope of the tangent, the positive slope, the negative slope, the zero slope. I feel like a weatherman. This is awesome. The straight, if the line is straight or if it has a curve to it. Area under the curve, we're not doing anything with that yet. We're going to get to where it stops, and then we'll ask, what does a uniform acceleration look like? So let's get a position versus time graph up here, just in the generalist of forms. Position in meters and time in seconds. Okay, position in meters and time in seconds. So from here, we are going to kind of see, we have this trend line, you know, that was gotten from some of our data here. Where the trend line crosses the y-axis, we refer to that as the y-intercept. Where the trend line crosses the y-axis, that is the starting value. Okay, the starting value. So what I want you to do is I want you to go back over and you're going to type in up to next to the y-intercept. You're going to type in the starting value, and I will do the same. So you can see right here, we're just going to get rid of that a, and we're going to write in the starting, I told you value, but you can also write in the starting position. Okay, that's where you're starting. All right, let's take care of the slopes now. So the slope of this line, we went over in class a couple days ago. The slope of any position versus time graph is the velocity, okay? So the slope of this line is the velocity. We could have a positive velocity, as we see right here. We can also have one that may have a negative slope or a negative velocity, and one that maybe just goes across and has a zero slope. Okay, so what do all of these mean? Well, simply stated, this is moving in a positive direction. This one is moving in a negative direction. This one is not moving at all. Oh, well, it's moving at a constant velocity, but it's neither increasing nor decreasing. So let's get those into words. We'll put those on the table. The slope of the tangent is the velocity. Okay, very important. A positive slope means that your motion is in a positive direction. A negative slope means that motion is in a negative direction, right? The slope corresponds with the direction. And a zero slope means you are not moving, okay? Your velocity is zero. If we're getting the slope from the line, and the slope of the line is zero, and that tells us the velocity, then the velocity also has to be 0. Okay? Next thing we're going to look at right down here, we're going to look at what happens if it is a straight line like we see here, or you might actually see a curved line, like this one. So we're looking to see what happens if it is a curved line, or let's see, this black one, black mark right here, is a straight line. Ooh, I'm sorry, you cannot see that. That is a straight line right there. I promise guys I will get better at this the more we do these videos, but cut me a little slack. I'm trying right now. So if anything else, hopefully you guys are getting a good kick out of this. When we have a straight line, we have a constant velocity. Now, if the line is curved, we have this curved line here. Let me put the color I don't have to use yet. The velocity here is one value. The velocity here is another value. The velocity here is another value. Notice we have 3 different slopes, 4 different slopes, 5 different slopes. So along that line, the velocity continues to change. So for that reason, when we have a curved line, we have a changing velocity. We don't have to write anything for area under the curve. We don't have to write anything for where the curve coincides. We stop when our line is horizontal. And then finally, what a uniform acceleration looks like, it is a parabolic line. And what that would be is something that looks, I'm just going to move this over, something that looks like this, and I drew it right below. So we have that parabolic. Okay, it's got a curve to it. All right, so we have everything done for our displacement versus time graph. Let's move over to a velocity versus time graph. Okay. So let me get up here and we're going to draw this velocity versus time graph. Erase this all out. So how are you guys doing today? Day off, got a nice break, right? Hopefully the weather's nice for you. Got any good plans? I mean, besides schoolwork, of course. Here's our velocity versus time graph, okay? Let's say we have some velocities here again, and we draw that line. The point at which the line intersects the y-axis is again the starting position. In this case, I apologize, it's not the starting position so much as it is the starting velocity. So let's go ahead and enter that into the top. That is the starting velocity. The next thing we're going to look at are the slopes. Now, these slopes are again similar to the displacement slopes, right? The slope tells us, and we're taking that step up with a position versus time graph, the slope gave us velocity. Now, with a velocity versus time graph, the slope will give us acceleration. Okay? So the slope of a velocity versus time graph gives us acceleration. From here, we can have a positive slope. Means we have a positive acceleration, an acceleration in the positive direction. Here we can have a negative slope, right, which means an acceleration in the negative direction, a deceleration, right? And then here we can also have the constant slope, which means, oh, sorry, they're all constant, but the zero slope, which means no acceleration. All right, let's go and add those to the 4 next spaces. We have the very top is acceleration. Then we're going to go down to a positive acceleration direction. a negative acceleration, and then 0 acceleration, or not excelling at all. All right, so hopefully you guys have kept up with all that stuff. Next thing we're going to add in is what happens if we have an acceleration that is a straight line versus an acceleration that is a curved line. Again, the acceleration, the slope, right? The velocity versus time graph, the slope gives us acceleration. If it is straight like this, that means we have a constant acceleration. If it is curved, we have a changing acceleration. Now, this is very important. Okay, this is the one and only time that we actually look at area under the curve. When we're looking at an acceleration, a velocity versus time graph, let's say it comes up, over, up, and back down. If we're calculating the area under the curve, that means we are multiplying the length times the width. You will be taking seconds and multiplying it by meters per second. Remember from math class, something on top, something on the bottom, they cancel. And in this case, you're left with just meters, which is your displacement. And in fact, calculating the area under the curve is calculating the displacement. Now remember, it is always area under the curve to the x-axis. If you had something drop below the x-axis, it would be the area under the curve to the x-axis. Okay? Let's add that in. So the area under the curve allows us to calculate the displacement. We can skip the nothing one where it looks at where the curve coincides. And then we will add in the final two. And those, the object stops when the velocity crosses the x-axis. And lastly, it is a straight line for uniform acceleration. All right, then the last thing we're looking at here is just the acceleration versus time graph. There's not too much we can actually pull in there. So for this one, we're going to look at just filling in up here, the starting position, it's the starting acceleration. And down here with uniform acceleration, it is a horizontal line. All right, so I hope you guys enjoyed this. I hope it helped a little bit. Let's see. So hopefully you guys enjoyed this. Hopefully it helped a little bit and it makes life a little bit easier understanding all this. Please, if you have any questions, email me, use Teams, and go through the chat section, okay? But by all means, get this stuff done and have a great day, guys. Be safe, and I will see you all in class tomorrow. Take care, everybody. Bye-bye.